Hello, hi, and welcome to another lecture of Physics2101. In the previous lecture, we started talking about rotating objects and their properties, and today we are going to continue doing that. So the next stop in our journey is section 10.4, kinetic energy of rotation. Now, for a translational object or translational movement, we said that the kinetic energy is K equals half mv squared. Very well. Now let's try to do that for a rotating object. Here's our object looked at from above. Here's our center. And I'm going to take a random point at a distance r1 and its tiny mass is m1. But then I can take another distance, r2, m2, r3, m3, r4, m4. The problem is, as we said, that depending on your distance from the radius, your velocity is going to be different. Now this gives us a problem. Which velocity of these do I use? Surely I cannot use any one of them. It would not give me the proper answer. So let's do the next best thing. I am going to divide it up into tiny m's and take the v of every single one of them and add them all up together. So half m1 v1 squared plus half m2 v2 squared and so on and so forth. Now, if I just generalize that for a second, I'll have half mi vi squared. I have something really interesting here that I can actually do. We already said that v equals omega r, correct? So I can substitute that. I get k equals half mi omega r, the whole thing squared. Now just rearranging that, omega is fixed for any point in a rotating body, so we can take it out of the sum. So we get half omega squared and then the sum mi ri squared, which I like to call miri squared or miri 2. Now this miri thing, we will see it over and over and over and over again, so much that we give it a name. We call it I. Okay, moment of inertia. It has a unit of kilograms meter squared, and it has two names depending on the textbook you're looking at: rotational inertia or moment of inertia. It's the same thing though. And now we can rewrite our very complicated looking equation in a very nice way. K equals half I omega squared. And already you can see the resemblance. Instead of m we have I, and instead of v squared we have omega squared. Let's take a look at a football. It's moving in a straight line. mv k equals half mv squared. What about if it's going on a circle? Well, I will have I omega and I'm going to have half I omega squared, where I is mi ri squared. Okay. Back to our table from the previous lecture, we're going to add one more line. M in linear motion, its friend in rotational motion is I. Okay, let's take a look at the same object we've been looking at. Now here's the thing. How do I calculate I? It's not a regular shape, it's weirdly shaped. I can do mi ri squared and add them all up, but it's going to be very, very troublesome. Instead, an easier way is, as usual, integration. I is the integration of r squared over each tiny mass dm. Now integrating that equation over a continuous body, okay, in principle we can always use this equation, whatever object we have. But it's not always nice, and especially it's not easy to define mathematically the boundaries of a weird looking object. So what we do is we have a set of common shapes that we regularly use over and over again, not only in this course but in general things as well. And the values for those have already been calculated, and it's given in your book in table 10.2 for common axes. Now here is a hoop when rotating about a certain axis, central axis, we have I equals mr squared. So we take the total m and we multiply it by the full radius, and that's it. If we have a cylinder about a central axis, so instead of something like this, more of something like that, well, we have, it's thick, so we have r1 squared plus r2 squared. Again, these are all derived from that integration equation, but we don't have to do the integration over and over again. We simply can use those values. You don't have to worry about exams. The equation sheet you have already has all of these. Here are some more. There's a whole bunch of them, which you can take a look at your own pace. Some more. Let's look at a PIQ. What is the moment of inertia of three spheres? We have three small spheres rotating about a vertical axis. It gives us the perpendicular distance, and it wants us to rank the three spheres according to their rotational inertia, biggest to smallest. Take your time, pause the video, try to do the calculation. Okay, here's some weirdly looking object with total mass m, and it's rotating about axis A. What is I with respect to axis A? We don't know. Looking at it from a different angle, yeah, still not very helpful. Okay, what if we found the center of mass? And we say that axis A is a certain distance from center of mass. Now, if you notice that in the previous bunch which we looked, they're always pretty much going through center of mass or center of some symmetrical shape. So we say, okay, we're going to try to find that of the center of mass, but then what? Well, turns out we have something called the parallel axis theorem. And what it says is, if I know my inertia at the center of mass, I can find it at any given distance that is h from that point. And it's given as moment of inertia, I blue, about any point is equal to ICM plus mass times that distance squared. How is this useful? Well, here is the disk that we saw a bit earlier. Well, now we know from the table that for a disk, it should be, let's see, thin disk rotating about this axis is 1/4 mr squared, but that is not particularly helpful. Disk or solid cylinder, the third one, if we take a look at it this way, half mr squared. About the center, we know it's half mr squared. So what is it about any other axes? Well, we just add mh squared. Let's do a sample problem. We have two particles and we want the rotational inertia about an axis through the center of mass, perpendicular to the rod. Well, m and m are the same. Distance is L. What is that of center of mass? Well, for very basic objects, we don't need to use those complicated ones. We can simply go back to MIRI squared. Each one of them is a distance L over 2 from my center of mass. And so it is m half L squared plus m half L squared, which is just half mL squared. What is the rotational inertia of the body about an axis through the left end of the rod and parallel to the first axis? Well, we can do MIRI squared again, but instead we're going to be doing it this time using the parallel axis theorem. We're going to take our half mL squared that we know already, and we're going to add plus 2m because m and m, and our entire length is L. But Our COM was already at half L, so the whole distance, the movement is half L, so half L squared. We end up with ML squared. Okay? Let's try another PIQ. Consider two masses, each of size 2m, at the ends of a light rod of length L with the axis of rotation through the center of the rod. The rod is doubled in length, but the masses are halved. What happens to I? Is IA bigger or IB bigger, or are they exactly the same? I'll leave it up to you to do. You can just use the equations in the previous slide. Another sample problem. Now what we're doing is, the idea is very simple, okay? But applying it can be a tiny bit problematic. So we're doing multiple examples to try and do as many as possible. So I have a few things. Now if you open your book, you have a sample problem 10.08. And I am actually going to try and do that right now. Sample problem. Ten 10.02, 10.04. And this is a very, very long problem. Let's see, long story short, in 1985, spin testing a sample of solid steel rotor, a disc, mass 272 kilograms, radius 38 centimeter. Sample reached an angular velocity of 14,000 revolutions per minute, and then there was a dull thump from the system. And they found that lead bricks had been thrown out in the hallway leading to a test room. So loads of energy, things were broken down. The concrete floor beneath the spin chamber had been shoved downwards by about 0.5 centimeters, and the 900 kilogram lid had been blown upward through the ceiling and had then crashed back onto the test equipment. The exploding pieces had not penetrated the room of the test engineers, only by luck. Good, so now we know how to solve the problem. Here's a photo, really bad. How much energy was released in the explosion of the rotor? So we want to figure out the explosion of the rotor, how much energy? Well, we go back here. Mass 272 kilograms. Radius is 38 centimeters. Velocity is 14,000 revolutions per minute. We're just writing everything down like we did in the tutorials. And we start converting everything into SI or SI-ish units. Okay? So omega is 1.466 x3 radians per second, and we want to know energy. Well, now it's easy. K equals half I omega squared. I for a disk is half mr squared. So half 272 times 0.38 meters squared, we get 19.64. And if we put those numbers in, we get 2.1 times 10 to the power 7 joules. That is a lot of energy. Okay, let's take a look at this door. And let's take a look at it from above. Now, I would have really loved to show you this in person in a lecture theater, but we have to do it as it is. We want to open it about this hinge. Simple enough. This is how a door opens. Now, here's the thing. Go to your nearest door of your room, of your house, and push as strong as possible at this end, at the closest end, and try to open the door. It might not open, and if you manage to open it, you had to push a lot to make it even move. On the other hand, if you try to move further away from the hinge at the other end of the door like we normally do, even a small child can, a very young person can open that door. On the other hand, try pulling the door from that side to open it, to make it swing. It doesn't matter how hard you pull. You might end up pulling the door off its hinges, but it's not going to rotate. Why is that? What is going on? The reason this happens is actually based in physics again, and we are going to describe it. The distance from the axis of rotation matters. Why? Because the force that you are putting on it is only one half of the story. The other half is how does it translate into rotational motion, and that is called torque. The quantity that indicates the ability of a force to cause rotation in the first place is called torque. So you could be pulling the door, okay, with 10 million newtons, it wouldn't rotate it because the torque would still be zero. Let's see. What if I push the door at an angle, F, some angle phi, a distance from the hinge, distance, let's call it R. Now, we have something called the line of action. Okay. Some new words, line of action, moment arm. Moment arm, let's actually write all of these down first. Okay, here we go. Now, once we write this down, we start knowing what's going on. It's similar to our idea when we're just looking at the components of forces, cosine theta, sine theta, mg sine theta, mg cosine theta when something was at an inclined plane. Now, the only bit of the force that actually works on torque, or that torque actually takes from the force, is that working along the moment arm, r perpendicular, r sine phi, or r sine theta. So definition of torque for us is r perpendicular F, otherwise known as r sine theta F, or in vector notation, which is the original definition, torque is equal to r cross F, a cross product from your chapter 3. Okay, remember, cross products are not interchangeable, so it's not F cross R, it's R cross F. Units, Newton per meter, or actually Newton meter, sorry. Now, let's look at our force. We have force perpendicular and force parallel. Force perpendicular is F sine theta, parallel is F cosine theta, and my torque is RF perpendicular. What's positive, what's negative in torque? Just like with velocity, counterclockwise, you're getting younger, it's positive, it's a good thing. Clockwise, it's negative. Let's look at a few examples. Here's the door. The moment arm and the lines of action are clearly defined. Now here, my torque is equal to RF sine theta, and theta is some angle. What about the second example? What is my theta here? The angle between the line of action and moment arm is simply 0. They're parallel. So my torque is going to be 0. This is why it will never work. If it's perpendicular, my angle is 90 and sine 90 is 1. So torque is equal to maximum torque, just RF. What about there? If I do it all the way there, my angle is 90, it should be torque max, but my R is 0. I am exactly at 0 distance from my rotation point. So my torque is again 0. Let's take a look at 3 PIQs. You're using a wrench and trying to loosen a rusty nail. Which of the arrangements shown is most effective in loosening the nut? 1, 2, 3, or 4? Or do they have all the same effect? Let's take a look. Number 1, you have a wrench, a nut, perpendicular, so torque max. Number 2, again torque max. Number 3, your torque is going to be reduced by some angle. And number 4, your torque is at an angle that is absolutely useless. So your correct answer will be number 2. You have maximum torque from the angle and a lot more R. This is why if you have ever seen a plumber work at your home, you will see that they usually use some really large sized wrenches. Okay, another question. I'll keep it on the screen for a bit for you to take a look at. And one more. And that's it for today. I hope this was useful. It was not a very long lecture today, but it does introduce some new and important concepts. See you next time.